Keep us on schedule. It's time to get started with the afternoon session. So welcome back from the abbreviated lunch break. And so now continuing on, our next invited talk, excuse me, is going to be given by Yunyao Li from IBM Research AI. And the title of her talk will be Towards Deep Table Understanding. So Yunyao is a distinguished research staff member and senior research manager at IBM Research, Almaden Research Lab, where she manages the Scalable Knowledge Intelligence Department, which focuses on building enterprise technology for AI applications. So she has built several systems while at IBM, and she's also a member of, she's an ACM distinguished member, and she is a member of the New Voices program of the American National Academies. So she's also written a book on natural language processing. So with that, I will turn it over to Yunyao to talk about Towards Deep Table Understanding.
Thanks very much, Doug, for the introduction, and thanks for everyone for inviting me to this workshop. So today I will talk about the work from my team toward deep table understanding. Before I talk about table understanding specifically, let me first talk about what is document conversion. I think for audience from this workshop, it's probably some problem everybody knows, but just in case anyone who need a little bit more background, so let me give a little bit more background here. So for document understanding, the resource are business document, like PDF, Word, and images. Those are files that are not directly easily digestible by downstream applications. The goal of document conversion is convert those content in an open text-based format such as JSON or HTML. Then they are going to be much more easily understandable by the downstream NLP AI applications. So why is the document conversion hard? So as some of you know, right, those kind of documents are designed for printing or for human consumption. There are a lot of information that are at the behind the scene, actually at a very low level. So in order to do the document conversion, we need to first be able to understand and preserve the reading order for all the different objects, from textual content to tabular and image content, similar way as how human being would read the document. And then they need to be able to identify and extract document structure such as the sections and the paragraphs and the tables and so on. And then for more complex document elements such as tables, actually understand the internal structure. So why document conversion is hard? First of all, there are really a few different sources of challenges. One is come from scanned document. The document itself, right, can contain a lot of noise, and then because of the scanning process, the text can be fuzzy and skewed. And then there are also nature of the text itself, right, could be colored background, which makes things even more difficult to capture. And then for table, for this important element from document, there are a wide variety of table. Often, because most of my research focus on natural language processing, but I often point out the fact that even though natural language itself is very hard, table is even harder because there is no rule for you how to create table, right? For natural language, there's a high level grammar that governs the whole thing. No matter how much noise introduced into natural language, there's still high level grammar. But for table, there is no rule. People create table for all kind of purpose with different ways, right? Here are just some examples here. And then finally, in document itself, there may be a variety of elements, right? We talk about table, but there could be charts, diagrams, signature, logos, and so on. Basically, we need to be able to identify all these different elements and then overcome the challenges or introduce further through the scan process. So within IBM, we do have a larger research, sorry. Oh, wow. Just a second. Yeah, within IBM, we do have a larger research agenda on deep document understanding, where our goal is to understand a complex document that could be scanned and contains visual elements like charts, tables, photos, and so on. And also the document can be very long itself and of different variety, right? Such as PDF manuals, technical guide, and so on. Our focus is really on converting those kind of challenging documents, because most of the cases, those are the ones that our customers need to deal with, and those are the ones matters the most in practice. So if you're interested in understand our overall research agenda, you can check out our recent blog on this topic. For this particular topic, I'm going to focus on table. As I mentioned earlier, right? Table is very hard, partially because it's very, very diverse. There are many different ways a table can be constructed. And what's the definition for table? So for table extraction, we define the problem in the following. The input is the document content in the native form, and the output is document content with tabular information where we identify the border. We also identify the cell within the table, and also identify the vertical and horizontal alignment of cell. And later on, I will give you an example of how do we even evaluate the output of table extraction. So if you look at this problem, you may think about, okay, this is can be very much formulated into a computer vision problem, right? We identify table and cell as objects, and when we can use deep learning network to detect tables and cells, problem solved. But if you look at it further, it's not so simple. So let's look at a few things, right? First, where do we get the data? Unlike in computer vision, where we have the existing like multiple data set, right? But the most famous one is probably ImageNet that you can leverage. For table extraction, not so simple. So when we start working on this problem, there was some data set available like ICDR 2013, ICDR 2019, and then Marmont data set. But if you look at each one of those, first of all, the data set is very, very small, right? So the largest one have a couple of 1,000 tables. Clearly, they're not sufficient to train a deep neural network. Then there is a more recent one called Table Bank. It has the 145K label table example. However, the label table only have logical coordinate. We cannot really utilize it for the purpose of training a model for table extraction. So as a result, we have to solve the data problem first. So how do we solve this problem? We actually created the two data sets from IBM. The additional ones we created internally, but the general approach is the same, where we look into publication data set, right? For example, for the PubMed, look at the PDF as well as the HTML, and then we do automatic text matching to create automatic label data based on those data sets. So the PubNet data set is available externally. You can take a look. Similarly, we built another one for the financial domain where the tables tend to be even more complex. So now we have hundreds and thousands of tables that we can actually make it possible to train a deep learning model. So the next question is, okay, there are already existing object detection algorithms and models. We can only just fine tune them, right, based on the label data. But it's not so simple. Let's look at this again. So if we think about traditional object detection task, right? The objects are generally of similar size. There is no obvious constraint between different objects, but tables are different. So tables and cells have very different size and aspect ratio, unlike the classic object detection classes. And it also has a nice property, which I will describe in a second, of how do we leverage that. In tables, cells are always inside table, right? Table always contain the cell. We cannot have table that contain no cell, and we cannot have cell that is independent of table. So this is a property we leverage in our algorithm called the global table extractor, where we have separate object detector for table and for cell, and then later on we introduce penalty loss so to actually enforce this constraint. So the penalty loss works the following. On high level is actually very simple, right? Look at all these potential candidates, and then if we apply penalty, if the detection is a table but contain very little cell mask inside the bounding box, and then if the detection is not a table but contains a lot of cell inside the bounding box, both are the cases that is unlikely to happen, and where we're going to introduce a penalty loss to avoid that. And later on, we can re-rank overlapping detection and making sure we rank tables that with a lot of cell inside over the ones that have very little cell inside. Yeah, so this is the part which we just described here. And then when table with similar confidence are overlapping, we also need to do some selection here. So essentially, we define something called the tableness, basically giving the bounding box how likely this is actually border of a table. So tableness is captured by a table candidate with a lot of similar region, and also not have similar region that just outside, but it's not being covered by non-overlapping region. So this allows to avoid having table that are that allows basically be able to rank tables in a way that favor the tables that have a lot of cell, and also be able to better penalize the cases where the tables are over splitting or over merging. So let's look at the results. If we look at the table border detection over ICDR 2013 and 2019, for both we achieve state-of-the-art performance. So this is for detecting table border. But then now when we want to look into inside the table, right? Another thing we actually take into consideration is that table come into different style. Once we identify the table boundary, there are further things we can do by looking into what's inside the table. If we look at the traditional object detection model, they focus on local area and do not really look at the nuances of different global table style. But this is a place where we want to do a bit more. On the high level, you can basically think of the following. We can cluster or classify a given potential candidate of a table to identify whether this is the ones that with the graphic line or the ones without for all the other table style. We can do further refinement. But on the high level, you basically want to say, we want to deal with the tables that are similar to each other in some fashion together to improve the cell boundary detection. And in this particular implementation, we focus on differentiating tables with graphic lines versus the ones that do not. And this, again, result in very good results, which I will talk about very shortly. On the high level, this is the kind of clustering we do is we sample at each box center horizontally and vertically to decide the number of the rows and columns in table. And then we also decide alignment for columns and row based on cell boundary box distance. Then we do k-mean cluster with number of center from actually step 1, 2 from each direction with coordinate depending on alignment, and finally we assign cell box to each row and column depending on alignment. The end result is, here are some example results. You can see that we are able to handle very complex structures where there is like nested header here, the same here. And then if we look at the evaluation metric called the cell adjacency relation, where the ICD 2013 match based on text and ICD 2019 match based on bounding box. Basically, those are all evaluating if the cells in the original table next to each other, they should also be output in the detected structure next to each other. So we can compute some recall and precision here. These are just sample results. I don't want to go into details on those. And again, if we look at the cell structure recognition, again, GT was able to achieve state-of-the-art results. So by now, maybe you think, okay, we are doing so well, right? We are state-of-the-art. We should be very happy about it. And but if you look at the difference, in some cases, the difference was not so significant. And one particular question I want to bring up is better really better? it based on all these numbers, right? We are doing well on all the data set and we are state of the art. But let's look at some more examples about how do they do evaluation. So let's look at a simple example here. So we have an original table from PDF, and this is the ground truth, right? It's a very simple table. Basically provide, and it's a toy example that we created for the sake of illustration. But you can see a lot of those kind of tables in financial documents, right? Provide revenue for different year, and then for different stock stick symbol. So let's now assume we have these two candidate table A and table B, right? In table A, what's the difference is in table A, it misses out some of the cells towards the end, and in table B, is miss out the column headers, the nested column headers. And in reality, this is actually more likely mistake to make because there is a white space here, right? So let's look at how we can compute those, evaluate those outputs. So the first one is, let's look at the table area. So for the table area, just identify the table boundary, right? Mostly based on the overlapping of the bounding box. So we can look at ICDR 2013 here, based on this number, right? If we look at the F1 measure here, table A is 0.88, table B is 0.9. Table B is slightly better than table A based on ICDR 2013 evaluation based on 2019, which is just evaluates the region, right? Remember, one is based on text match, the other based on bounding box match. One is better than the other. But in both cases, I think they are very similar, right? And then look at the second metric called the cell adjacency. So here, based on cell adjacency, because table A misses out more cells, other result, for cell adjacency, it performs much worse than table B. However, my question is it really the case that table B is a more desirable output than table A? Let's look at the downstream application, right? So some of you may be aware There is a paper called the methodology for evaluating algorithm for table understanding in PDF document. In this document is actually talk about the two metrics of table area and cell adjacency. Then there is a third metric called a functional metric, which evaluates how well the converted table preserves the semantics for each of the data cell. Think about semantics in our particular toy example is giving, for example, the number 11.0. What does it mean, right? So in order to understand this particular cell, we need to understand this is the revenue number for 2008 in terms of billion, and for stock symbol LUV. So that's how you can recover the entire semantics. So we can recover this semantics from table A because the column header are there. But then this information is completely lost from table B. In table B, you can only know 11.0 is something related to LUV. But the fact this is the revenue in the unit of billion for 2008, that completely lost. That's why when you look at the output for candidate table A, the functional metrics 0.86, but for candidate table B, this is not there. And the F1 measures all there. So this is a very important thing I want to bring up. The reason we cannot really compare functional metrics with other competing systems is that right now, as far as we are aware, there is no labeled data that we can actually use to do this kind of comparison. It's very unfortunate. But in reality, what we want to achieve is not just achieve state-of-the-art on public benchmark data set, but also significantly outperforming our competitors on data and metrics that matter. We have some internal evaluation and that demonstrate on the data set that matters to some of our customers. We are able to achieve this goal. But right now, to be honest, we don't really have a data set that can systematically do this evaluation in larger scale and that allow us to share any numbers externally. So now basically I have introduced the GTE, which is a very powerful, I would say relatively simple, but a very powerful model to solve the problem related to table. However, another question is, can we make it better? Like we are state of the art, we work out of box very well, but more often than not, right? Our customer want what we create works the best for their use case. So now the question is, how can we make it work better? Our answer is that we can allow you to retrain GTE with interactive labeling. So rather than ask people to label again hundreds, thousands of tables, which there is another paper actually on why ground truthing for table is very hard. We don't want people to do that. So instead we create something called the TableLab that allows the user to inspect the output of GTE and to be able to correct the output through a very easy to use UI, and then the corrected table will be used as the label to retrain the GTE algorithm. The main high-level innovation here is that we're not asking the user to randomly label things. Instead, we take a more of an active learning approach. We will identify tables that our system is least confident ways. Then when the user do labeling, we also propagate those labels for tables that look similar to the one already labeled. If you're interested, you can check out our IUI paper. And in the end, this is turned out to be a very useful approach. So we're still running larger scale evaluation, but our initial evaluation based on 20 pages actually 100 pages with 20 pages for each category, where 10 page used for retraining, 10 page used for testing. As you can see, with just a relabel of 10 pages, we can increase the both table boundary detection and cell adjacency by as much as over 100%. So this really illustrated the power of retraining when we have an intelligent way to solicit label and also have an intelligent way to augment the label data automatically. So now you may be wondering, table is great, but what can you do with table? Table actually are extremely powerful. So here are some examples. For research and social goods, we actually have done multiple work in this area. Last year, when maybe some of you have looked into this, when COVID-19 come out in March by AI tool, the first time we look at the data, there is no any information related to the table. And then later on, when we found out from AI tool, two things. One is they did not include table because it was too hard, which is not surprising at all, right? Second thing is that table is the most requested feature on their cargo competition. That's why we quickly partnered with AI tool, and then since May 12 last year, COVID-19 has table information. So that's all thanks to the GTE capability that we described earlier, and also people like Doug from my team working very closely with AI to make that happen. Another thing is within IBM, also, I think sometime in May or June, we pushed out this COVID-19 data dashboard. And again, around that time, there was a lot of information available in API or CSV file. Instead, a lot of information published on, in PDF format by different county. Because we have this very powerful table extraction capability and also followed by table understanding capability, our developers were able to quickly build COVID-19 dashboard in less than a week. Also, some of our colleagues work with us on enable TableQA that allow people to search and get answer from individual tables. And we are also working with climate scientists to look into how can we better understand historical record related to the past couple hundred years of the climate, so that we can better understand the current climate change. So this is a very powerful capability because a lot of the information resides in table. And that's very surprising, right? There are a lot of use cases in business too, like think about understand invoice, understand purchase order, understand a contract. Those are all the capabilities that is powered by what I just described earlier. So finally, I think based on my presentation, hopefully by now you can appreciate the importance of table from PDF, and also you have a reasonable understanding of GTA capability and TableLab. But I will say we're just at the beginning of this. In fact, our team working on table since 5-6 years back, and GTE just the latest work we have done. The fact we're able to quickly adapt the object detection literature to handle table is really because we have working on this area for years and understand the problem very, very well. But at the same time, this is a very challenging problem. We have getting somewhere, we're getting to the point where the capability is production ready and used by many people. But at the same time, there are many open challenges. On the quantity side, as I said earlier, right? Even though we are state of the art based on the metrics people define externally, in reality, we need to work nearly perfect on every single thing people give to us. We're not there yet. We need to be there. And then runtime performance, right? How do we process hundreds, millions of the documents at the speed? That's still a challenging question, especially with a expensive deep learning model. And customizability, we have some solution, TableLab, but I'm sure there are additional ways we can enhance it. And then evaluation, like there is a reasonable metrics defined, but never used in practice. How do we leverage those kind of the metrics and also creating data set to making automatic evaluation possible? And finally, document conversion or table understanding, they are never done in isolation from downstream task, right? So if we understand the downstream task better, can we leverage that understanding to improve the entire end-to-end process by leveraging something like multitasking learning? So those are the things that we hope to explore, and this is something we're going to continue working on in the future. Yeah, thanks everyone. That's the end of my talk.
Okay, thank you, Yunyao, for that talk. So I guess we have some time left for some questions. Let's see. So Dave has a question. Dave Lewis.
Hi, great talk. I was curious about the type of feedback that users give in TableLab. I wasn't entirely clear. Are they correcting the structure that was extracted, or are they just saying yes or no, it's good or bad, or what sort of feedback is it?
Sure. Yeah, great question. So let's look at the screenshot here, right? So what they can do is two things. One is they can say good or bad, but they can also do additional correction. They can, for example, merge cells together or do split. They can move. They can also add new cells, like new element. So essentially, they can actually relabel the whole thing.
And so in practice, what do they do? And I guess also just, I mean, what was their job? What motivation do they have to give feedback?
I think, so this one, we still need to do a bit more user study. I would say right now, the way TableLab has been used are two things. One is people actually use this to do full annotation to create a benchmark data set, because this is a much easier to use UI than some of the other annotation tools out there for table. So that's one part. And the second part, when people use this for customization, what they do is they label, like actually, as I showed earlier, they label a few pages, and then they look at the output. If the output is sufficient, that's basically about what they do.
Great, thank you.
Yeah, because our users are motivated to give us good data. Most of our users so far are developers of particular application. So they want our data works for their use case. I think there are some questions in the chat.
Okay, yes. Yes. Yeah, so, it was just about the availability of the slides.
Yeah, so for the slides, I will, normally for all my external slides, I will share on my slide share. So I will probably make it available later today or tomorrow. You can also follow me on Twitter, which I will send that announcement when the slides are available.
Great. So I have, I guess, one question sort of related to this, and it kind of comes down to the metrics, and what Oh, actually, let me, okay, so somebody actually, let's go to the actual question from the audience. So could you please expand why the F1 score for cell structure can be 24 with the 2019 data set versus 96 with the 2013 data set? So I believe that was the F1 score on the...
Yeah, I think it was a few slides earlier. I have two screens, kind of need to move. Mouse here. Yeah, so here.
Yes, that one.
Yeah, so I think the question was that here, we have 90 something, and then here we have 20 something. So let me come here. The main thing is for 2013, the match is based on text. So the bounding box is not really important. Another text, the match is based on the text, right? So if you think about the example we gave earlier, here the bounding box can be very small or can be very large, but the text is, another text is the same, is considered a match. But then for ICDAR, the match is based on the true, like the original bounding box. So think about if I tend to be very conservative, only for instance, let's say for this last cell on the second row, right, the 400 here, you identify very tight bounding, like very tight bounding box there versus the actual original bounding box. You're going to be penalized, even though it's actually not, from downstream point of view, it doesn't really matter, right? As long as you identify this 400, whether you identify the white space around it or not, it doesn't matter. But in ICDAR 2019, you're going to be penalized by that. Does that make sense?
Yes, thank you so much.
Yeah.
Okay,
So actually another way of evaluation I didn't really mention here is that the two kinds of evaluation or two type of evaluation metrics, right? One type is for the purpose of the developer of those models to be able to say how well is my model doing, where you may want to introduce many metrics. Like you want to look into how well I'm doing in terms of table boundaries, cell structure, and maybe some other things too. But then there is metric that matters for downstream application. So in reality, for example, for our document conversion, we actually have a definition of 70, 80 metrics that allow the developers to look into every single aspect very carefully and to be able to refine their models. But then for reporting to our offering manager, product manager, we report on metrics that matters from downstream point of view. I think that's important to think about when we think about the competition. It's okay to have metrics that matters more from model development point of view, but eventually this is consumed by someone else. We need to have metrics and data that reflect the use cases.
Oh, let's see. So Shaiwen Chen has a question.
Yes. Hi. Thanks for the very nice talk. So this is Shiwen from Apple. So my question is for the table. So I think one key metric in our use cases for downstream task is, for example, for each cell, we want to know whether the column key or row key has been correctly identified. Which means in downstream we want to know, for example, is that the accurate right? For example, for the AAL, what's the revenue essentially, right? Especially we observe a lot of challenges in the nested keys. For example, there's challenges for the nested row key or column key. Can you give some comments on that, how to solve that challenge? Thank you.
Yeah, that's a very good question. I think a few different things we need to think about here, right? First, we need to identify whether a cell is a data cell or or a header, right? Column header or row header, and then the nesting. I would say in general it's very hard. There is a metrics, right? Like the functional metrics aim to design to capture that. The functional metrics will reward like identification of the full, what are they call access paths. For every data cell, there is an access path that basically understand the entire nesting. So here, I think we have a relatively simple table where the row header do not have nesting. But in reality, like for financial table, the row header themselves can have nesting. And that just annotation on its own, I think is very hard. And then assuming you have in annotation, then you really need to making sure you have the right metrics to evaluate that. In terms of actually addressing, like identify the nesting, I would say in general, if the nesting is explicit, right? Where, for example, when you look at it here, I think the nesting you can view it as the explicit, where it's clear 2028 and 2008, 2009 are nested by revenue. But then sometimes it can be implicit, especially for row header, where you can have a row where everything else is blank, and then only the left-right cell have a name, and then everything else is indented, and that basically implicit nesting. That basically you can do a few different things. One is you can identify the nesting relationship here in table extraction, but in most of our cases, we should do some of this kind of work as downstream table understanding time, where when our goal here is to faithfully capture those kind of information, and then the interpretation of something as nested header is done later on in table understanding from the converted HTML file.
I see. Thank you.
And okay, yeah, thank you for the great questions. And I want to thank our speaker, Yunyao, one last time for that really great talk on towards deep table understanding.